So I have a claim about this first one here. You've done this before, and you're looking at this thinking, no way. And I'll say, yes, you have, because the key to success with working with any kind of inverse trig function is understanding that anytime you see an inverse notation, that represents an angle. So I'm going to call alpha this, and I'm going to call beta that. And what we know from that is that sine of alpha is 1/2, and I know that cosine of beta is 3/5. So we're asking in a roundabout way, what is the value of sine of alpha plus beta, knowing this information? And that should look familiar from your work with sum of difference angle formulas. So we know that we're dealing with two triangles, and since the ratios are positive, we know that we're landing in the first quadrant. So this means sine of alpha is 1/2, and that has another side of √3. And this other one tells me that cosine of beta is 3/5 with an unknown side of 4, Pythagorean theorem again. Now, we have all that set up again. Remember what this all means. Well, this means that sine of alpha plus beta, using the identity, is sine alpha cosine beta plus sine beta cosine alpha. Look at that. So we have values for all of these. We were given some of them. Sine of alpha is 1/2, and cosine beta is 3/5. Sine of beta, well, looking at the beta triangle, sine of beta looks like it's 4/5. And cosine of alpha looks like it's √3/2. So I'm looking at that, and both of my denominators are 10, so I can just combine these as one fraction. 1 times 3 is 3, and 4 times √3 is, well, as it says, 4√3. And there we have it. So there's the exact value. Now, if you want to check this on your calculator, you absolutely can. You have to be a little bit more creative about it, though. So let's bring this up here. So I'm going to type in the original expression before we touched anything. So sine inverse of, I'm just going to call it 0.5, plus cosine inverse of, I'm going to call that 0.6, and I get that. Okay, now I'm going to take the value that we got, which was parentheses 3 plus 4 square root 3, all in the numerator, divided by 10. And look at that, we have a match. So that kind of that verifies that our answer is correct. Okay, so there we have it. So that's finding an exact value of 1. Now let's look at an expression. So keep in mind the directions here. We want to avoid having a trigonometric function in the answer. So you're probably thinking, how is that going to work? Well, let's just follow along with it. So again, inverse tangent of something is an angle. So I'm going to call this alpha. So we know that this means that tangent of alpha is x/2, and our goal is to find sine of alpha. So we can pick it apart that way. And when you think about it, we've done this before. It's just not been presented to us this way. So I'm going to assume that we're in the first quadrant again. Tangent of alpha, well, alpha is the angle, so we have tangent opposite over adjacent. And if we do the Pythagorean theorem correctly, we know that this side's going to be x² plus 4 under a square root. And what that means sine of alpha is x over the hypotenuse, square root x² plus 4. And there we have it. So applying trig functions to inverse trig functions, we don't have to have the trig functions in there. This form looks yucky. This form looks more workable. This is also called the algebraic form. So we have trigonometric form that's going to have any one of the 6 trig functions in it. We have algebraic form that's kind of back from the good old days before we learned about the trig functions, right? So this just shows you that there is a link between the two. So I hope that you have a better understanding of inverse trig functions now. Thanks for watching, and stay tuned for more later.